Hello, today we'll be discussing two very important equations of solid mechanics, namely the equations of equilibrium and the continuity equations. Firstly, we'll look at equations of equilibrium. To discuss this, let's go back to the compatibility equations. In compatibility equations, we considered the strain compatibility, which ensures the continuity of material. Similarly, when we consider stresses on a body acted upon by different kinds of forces, it is important to consider the equilibrium for every part of that body. And the equations of equilibrium essentially gives that. So let's look at that. If we look at figure 1 gives the state of stress at a point considering a small element, and the stresses shown here balances each other on all sides. For example, if you look at the left-hand side of this cube, you have got sigma x going from right to left, sigma xy going downward, and sigma xz going towards the origin. And if you look at the right-hand side of this cube, right-hand face of the cube, you have got sigma x going from left to right, which balances sigma x on the left-hand side of the face. And similarly, tau xy and tau xz are in the opposite directions of the shear stresses on the left-hand face. Similarly, if you look at the stresses acting in the y direction, sigma y and the two shear stresses, you will see that they are balancing each other. Sigma z is also shown here, and sigma z on the other side is not shown here to make it look a little simple. So essentially, this figure tells you that on a single element, the stresses balance each other. But when we look at an elastic body subjected to external forces, including body forces and or surface forces, every part of the body must be in equilibrium. Here, before we start looking at the equations of equilibrium, I like to mention one thing: the body forces. Body forces are nothing but the field forces, such as the gravitational forces, magnetic forces, electrostatic forces, and surface forces too. Here, we consider the small changes in stresses across the element. This we did not do in figure 1. But to consider the equilibrium of every part of the body, we must consider the small changes in stresses across the body. Let's look at figure 2. Figure 2 essentially shows that if you look at the left-hand face of this cube and the right-hand face of the cube, you will see that the stresses have an increment in the x direction. For example, sigma x on the left-hand face has increased on the right-hand side, right-hand face, that is across the element, by an amount del sigma x by del x into delta x. This is a typical way we consider the increment, as we have seen before. Del sigma x by del x is a rate of change of the stress multiplied by the length over which it is changing. So the stress sigma x has changed to sigma x plus del sigma x by del x into delta x. Similarly, tau xy, which was acting downward here, will be acting upward here to balance, but there is a small change, tau xy plus del tau xy delta x. They're all changing in the x direction, and hence the rate of change is with respect to x. Similarly, tau xz, it was acting towards the origin, and here it is acting away from the origin, and it has an by del x into delta x. The same thing is shown in the y direction. Sigma y in the bottom face is acting downward, whereas sigma y on the top face is acting upward to balance, but there is an increment. Sigma y plus del sigma y by del y into delta y. And tau yx or xy is acting from right to left here, but on the top face it is acting left to right, but with an increment tau yx plus del tau yx by del y, because it is acting in the y direction into delta y. In the same way, tau yz has an increment of tau yz plus del tau yz by del y into delta y. In the similar way, the stresses in the z directions have an increment, but this is not shown here to make the figure simple. Now look at the equilibrium of the element in one direction, say for example, x direction. So there are three main stresses in the x direction: sigma x, tau yx or tau xy, and tau xz, which is not shown here. So what is the net stress on the element in the x direction? Sigma x plus del sigma x by del x into delta x, del sigma x by del x into delta x, minus sigma x, which must be subtracted because it is acting in the opposite direction. And it is acting on an area of sigma y into sigma z. This Q, remember, is of size delta x, delta y, and delta z. So the area on which this stress is acting is delta y into delta z. Remember, equilibrium can be considered only for forces, not for stresses. So we have to convert the stresses into forces. That's what we have done here. Now consider tau yx or xy. So tau yx has changed to tau yx plus del tau yx by del y into delta y. So we write here del tau yx plus del tau yx by del y into delta y minus tau yx, because that is acting in the opposite direction. And what is the area it is acting on? Again the same thing. This area is delta x into delta z. Delta x into delta z. Similarly, the stress tau xz, which is not shown here, will have increment tau xz plus del tau xz by del z, because increment is in the z direction, into delta z minus tau xz, because that is the original stress acting in the opposite direction, and the area on which it must be acting is this area, this area. And this area is delta x into delta y. So these are the total force due to the direct and shear stresses. In addition to that, we'll have a force due to the body force. Now, body forces are usually shown as X, capital X, capital Y, and capital Z as body forces per unit volume. So if we want to show that here, we have to multiply X with the volume. And the volume is simply, volume of this element is delta X, delta Y, delta Z. Now this is the total force acting on the element. And this must be equal to mass into acceleration. What is the mass? Suppose rho is the density of the element and the volume is delta X, delta Y, delta Z. So this is the mass of the element, and Fx is taken as the acceleration in the x direction. So this is the total equation of equilibrium in the x direction. We have taken the forces in the x direction and equated it to the mass into acceleration. Okay, so this is the first equation of equilibrium. Now let's try to simplify it. We rewrite that equation here and try to simplify it. How do we simplify? Here sigma x and sigma x cancels out, and we are left with del sigma x by del x into delta x. And if we take the bracket out, you will have delta y into delta z. So you have got del sigma by del x into delta x, delta y, delta z. So that is the first part of the equation. Del sigma x by del x into delta x, delta y, delta z. Second part of the equation again, tau yx and tau yx will cancel out, and you are left with del tau xy, yx by del y into delta y, and outside the bracket you have got delta x and delta z. So you have got del tau xy I have written because xy and yx are the same thing. Del tau xy by del y into delta y to delta x and delta z. So that is the second part of this equation. And the third part of the equation again, tau xz and tau xz will cancel out, and we are left with del tau xz by del x into delta z, and outside the bracket we have got delta x and delta y. So we are left with del tau xz by del z, delta y, delta x, delta z. So these are the simplified forces due to the stresses. Now in addition to that, we have got body force, which is x times delta y, delta x, delta z, and equal to the mass into acceleration, rho, delta y, delta x, delta z into Fx. Now in the next step, we cancel out this volume term. You will see that in all the parts, this is the common thing. Delta x, delta y, delta z, which is basically the volume. So if you cancel out this volume term from all the parts, this one goes out, this one goes out, this one goes out, this one goes out, this one goes out. So you are left with del sigma x by del x, del sigma x by del x, del tau xy by del y, del tau xy by del y, and del tau xz by del z, del tau xz by del z plus x is equal to rho fx. Now, There is a wonderful symmetry here if you look at it carefully. If you look at the stress tensor, the first row is, if you remember, sigma x, tau xy, and tau xz. So all we have done is we have derived them with respect to three different variables, that is x, y, z. So it is very easy to remember the equations of equilibrium, which is del sigma x by del x, del tau xy by del y, plus del tau xz by del z, plus x equal to rho fx. Similarly, if you look at the equation in the equilibrium in the y and z direction, you will get similar equation. And if you, easy to remember if you look at the second row of the stress matrix. So that will be del tau x, yx or xy, del tau yx, del y plus del x, del tau yx by del x plus del sigma y by del y plus del tau xz by del z plus y is equal to rho fy. I will repeat this for you to understand it easily. Remember the stress matrix. Stress matrix second row is tau xy or tau yx, sigma y, and tau yz. So all we have done is we have derived this with respect to x, y, and z in three different columns. So it is del tau yx by del x plus del sigma y by del y plus del tau yz by del z plus y is equal to rho fy. In the same manner, we can look at the third equation of equilibrium, which is del tau zx by del x, del tau zy by del y plus del sigma z by del z plus z equal to rho fz. Again, easy to remember if you look at the stress matrix. The third row of the stress matrix is tau zx, tau zy, and tau sigma z. So it is del tau zx by del x, del tau zy by del y, plus del sigma z by del z, plus z is equal to rho fz. So these are the three equations of equilibrium, and these are the very important equations, and it has to be satisfied in all solid mechanics problems which requires equilibrium. So we rewrite it here for ease of understanding. So let's go through it again, and for understanding and remembering this, remember the stress matrix, and we can easily write the equations del sigma x by del x plus del tau xy by del y plus del tau xz by del z plus capital X, which is the body force, equal to rho density into Fx, acceleration in the x direction. Second equation is del tau yx, second row of the stress matrix, del tau yx by del x plus del sigma y by del y plus del tau yz by del z plus body force in the y direction, capital Y, is equal to rho, the density, and Fy is the acceleration in the y direction. Similarly, the third equation will be del tau zx. Again, remember the third row of the stress matrix. And we have got del tau Zx by del x plus del tau Zy by del y plus del sigma z by del z plus capital Z, which is the body force in the z direction, is equal to rho, the density, and Fz is the acceleration in the z direction. So these are the three very important equations of equilibrium in solid mechanics. Now we go to the next important set of equations, which are the constitutive equations. Constitutive equations basically gives relations between parameters or quantities that are required in solving solid mechanics problem. So we say that the relations that characterize the physical properties of material are called constitutive equations. So here, remember, this physical properties of material is important. Now, if you look at the physical properties of material, there are enormous physical properties, and there are very different ways they can be loaded. So to choose a constitutive equation is difficult. Which physical properties you take and which kind of loading you take. To make it easy, in this course, or in many simpler analysis, we usually choose a model based on linear elastic solid. And the mechanical behavior of the solid is defined by the constitutive stress-strain relation. Actually, these are the important things in solid mechanics: stress-strain relation and the linear elastic solid. Now, I want to say one or two things about linear elastic solid and the stress-strain relation. I think we all know about the stress-strain relation, even from the school age, that sigma is equal to E epsilon. Sigma is the stress, and E is the elastic modulus, and epsilon is the strain. Now, this is a linear elastic, true for a linear elastic solid, because sigma and epsilon are varying linearly. But if you want to have a nonlinear behavior, how will you write it? It's very simple. You write sigma is equal to E multiplied by epsilon to the power n, where n is not 1, not equal to 1. So then it becomes nonlinear. And there are very many materials which behave nonlinearly. No. But we'll not go into that. But if required, we can easily go into this by introducing this instead of this. Now, this is a simpler way of stating the constitutive relation, but a generalized Hooke's law or generalized constitutive equation has to be in more general term. And there, look at this little carefully. Instead of sigma, we write stress matrix, that is sigma ij. And instead of epsilon or strain, we write the strain matrix. Because stress and strain at a point is given by stress and strain matrix, as we have discussed before. So if we look at this in a tensorial form, this is the stress tensor, this is the strain tensor, and they are connected by a constitutive tensor. This is called a constitutive tensor, Dijkl, and where K summation of Dijkl, K 1 to 3 and L 1 to 3. So to summarize it, the constitutive equation for stress-strain relation or the generalized Hooke's law is simply stress tensor related to strain tensor by a constitutive tensor, and this is the constitutive tensor. Constitutive tensor is nothing but a fourth order tensor Dijkl. Now, this constitutive tensor depends on many different properties of the material. So if we consider the vast number of properties, then the number of constants will increase and the form of the constitutive tensor will be different. So let's look at this in a very simple form. In fact, if you consider the total number of material constants in a generalized Hooke's law, it will be 81, because 3 to the power 4, there are 4 different variables and they are all from 1 to 3. So it is 3 to the power 4. But since the stress and strain tensors are symmetric, then it comes down to only 36 for anisotropic materials. Anisotropic material means that the material properties vary in different directions. Properties in x direction, and y direction and z directions are different. In that case, we can write the constitutive equation in a very simple way. That is, we write the stresses in a column matrix, sigma x, sigma y, sigma z, tau xy, tau yz, tau zx, and strain matrix in a column matrix, epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, gamma zx. Earlier we have written epsilon xy, epsilon yz, epsilon zx. In fact, it is right to write, it is correct to write as gamma, as I pointed out earlier. Anyway, so this is the stress matrix, stress column matrix, and this is the strain column matrix. And they are connected by the constitutive matrix, which is a 6 by 6 matrix. And hence, the number of constants are 36 for anisotropic material. But even this is difficult to handle. And this is why various assumptions or various conditions are imposed, and we'll briefly look at them. If you introduce an energy density function, I will not go into the details of this. This is a special function. And if you do that, then the number of constants come down to 21. On the top of it, if you introduce the condition that the material with one plane of symmetry, then the constants come down to 13. If you then take orthotropic materials means material properties vary in different directions. Then the constants come down to 9 only. But if we make even further assumption, such as homogeneous and isotropic material, which we do normally in our usual engineering problems, homogeneous means properties are same throughout from point to point, and isotropic means they are same. Iso means same in different directions, isotropic materials. Then the elastic constants come down to only 2. This is very interesting. What are those 2 constants? E and nu, which all we know very well. And here, the constitutive equations comes down to a very simple form. We can write it even without going into the tensorial form. We can write it by looking at the Poisson's effect. We can write epsilon x is equal to sigma x by E, which is quite obvious, minus the effect of sigma y and sigma z, and that will be multiplied by nu, because if you pull a body in x direction, only sigma x will contribute to the stretching. Other two stresses will try to compress or reduce. So we have got, I think this idea is known to all of you. Epsilon x is sigma x by E minus nu sigma y by E minus nu sigma z by E. So these are simple equations which I think is known to all of us. Then we can write epsilon y. Epsilon y, only the positive term will be sigma y by E, and the other two will be negative, that is minus nu sigma x by E minus nu sigma z by E, because they are acting in the opposite direction to the sigma y. Similarly, epsilon z, which is the strain in the z direction, there will be only positive part will be sigma z by E, and other two will be negative, minus nu sigma x by E minus nu sigma y by E. These are the effects of, these are the equations related to the normal strain or the direct strain. In addition to that, we have got shear strain. Again, here I have written in terms of gamma for ease of understanding. Gamma xy is nothing but tau xy by G. G is the shear modulus. And gamma yz is equal to tau yz by G. Again, G is the shear modulus, and gamma xz or zx is equal to tau zx by G, which is again the shear modulus. And the elastic modulus and the shear modulus are related like this, which you, I think you have learned it in your earlier lessons. So here we have got 5 equations which are the basic constitutive equations which can be written without looking at the generalized form, tensorial form of the Hooke's law. This comes easily just by considering the Poisson's effect. Now let's look at equation 2 with respect to 3, 4, 5, 6, and 7. That means how do we put the values of D11 to D66 in view of equations 3, 4, 5, 6, and 7. Okay, so let's go there. We have got the strain matrix on the left hand side, epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, gamma zx. Now here we are writing strain to stress, and the constitutive relation will be accordingly. We are writing this to follow these equations. If you look at epsilon x sigma x E has been taken out, 1 by E. So you have got sigma x only, and sigma x is already there. You have got only 1. And the rest of the parts are E is taken out. So it is minus nu and minus nu. Okay, so this equation is followed here in step by step. So epsilon x will be, first term will be sigma x is here. So 1 minus nu, because E is taken out and sigma y is there. Sigma y is effect is negative and sigma z effect is also negative. So 1 minus nu minus nu. No shear effect, so these are 0. Similarly, if you look at epsilon y, you will see that the first term is negative. So you'll have minus nu because E has been taken out. And the only positive term is sigma y by E. So it will be 1. It will be 1. And the next term will be minus nu. And no shear term, so they are all zeros. The third equation, epsilon z, again, there are first two effects are negative, so there will be only nu effect or Poisson's effect, so minus nu, and the third one is positive and 1, and the shear stress terms are 0. Now if you take the gamma xy, there is no normal stress effect, and there is effect of only one shear stress, that is tau xy. So tau xy is here, and it is 1 by g. In 1 by g, if you express it in terms of this, it becomes 2, 1 plus nu by E. And E is taken here, so you have got 2, 1 plus nu. In the same way, gamma yz will be, direct strains will be 0, and the gamma xy term is also 0. No other shear strain effect is there, only tau yz effect is there. So tau yz is there, and 2, 1 plus nu. In the same way, gamma zx, everything is 0 except the tau zx term will be 2, 1 plus nu. So this is how we can relate the constitutive term, constitutive equation 2 to our simple analysis. And this is the constitutive equation of strain to stress. But if you want to find out the relation or the equation for stress to strain, then you have to convert this equation in terms of sigma x. That means write sigma x, sigma y, sigma z in terms of epsilon x, epsilon y, epsilon z. That is not very difficult. There are 3 equations and 3 unknowns. You can work it out. And if you work it out, you will find out that the constants become like this. I will leave it to you to work it out. It's not very difficult. And then you get equation 9. So in brief, what we have learned here is that there are stress matrix and strain matrix, and they are related with a constitutive matrix or constitutive tensor. Now the constitutive tensor can be of different order, and the number of constants may be different. But usually for anisotropic material, we take a 6 by 6 matrix, and stress to strain matrix is related to by a constitutive matrix, and this is sometimes called stiffness matrix. Now to find out how the D11 and D66 vary, we look at simple relations for homogeneous and isotropic material of equations 3, 4, 5, 6, and 7. They're all known to us. And if we look at it, then we can easily find out the values of D11 to D66 by comparing the equations with the matrix. And it comes out in a very simple form, equation 8. And if you want to convert this equation to stress strain relation, then the constitutive matrix will be different. There you have to write sigma x, sigma y, and sigma z in terms of epsilon x, epsilon y, and epsilon z. It's not very difficult because you've got 3 equations and you can convert this. And if you do this, you'll get an equation like this. I'll leave it to you to work it out. It's not very difficult. And that will give you equation 9. So that's all for today. And we'll discuss more later on.